All right, guys, let's talk about Lewis dot diagrams. Lewis dot diagrams are really important. You'll see why. And what it is, it's just a diagram of the valence electrons in a neutral atom. As you know, valence electrons are found in the valence energy level of an atom, and they are the outermost electrons of a neutral atom. And those electrons are particularly important because the behavior of those valence electrons dictates the chemical properties of each element. Okay, so let's take a look at what this ends up looking like. Lewis diagrams are really easy, actually. So here we have a Bohr model of an atom. This is a neutral atom of phosphorus, and one of the ways that you can know that from looking at this Bohr model is to count the number of electrons that are present. And that number of electrons, as long as we know it's a neutral atom, that is going to match the atomic number. So if you counted these electrons in these three energy levels up, it would be 15 electrons, and that is the atomic number of phosphorus. And so the electrons that we care about are the ones in the outermost energy level, these 5 valence electrons. And a Lewis diagram just basically forgets about any electrons that are not part of the valence level, and we just diagram the outermost electrons. And so this is the Lewis dot diagram for a neutral atom of phosphorus. And you can see hopefully that these 5 here on the outermost energy level, those are the 5 electrons represented around the phosphorus elemental symbol, okay? So the way you want to do is surround the element symbol with the appropriate number of valence electrons. And there's a way that you do this, but before we get into how this is done, I want to explore the periodic table just a little bit. So here's a little periodic table, and remember that we're kind of forgetting about everything below the 3rd energy level for now, especially this stuff on the inside. We're just focusing on the first 3 rows of the periodic table, okay? And so I want you to picture, like here is the first, here's the first column of elements: hydrogen, lithium, and sodium. And you can see that they're all very different sized atoms, but they do have one thing in common. They each have only 1 valence electron. And if you look close at this, these Bohr models, instead of a dot here, I've used the element symbol, but the rings around the symbol represent the energy levels. And so hydrogen just has 1 valence level and 1 valence electron in that level. And then lithium's got a second energy level with 1 valence electron, and sodium has 2 completely full energy levels, and its third is its valence level with 1 electron. And so they're arranged in these columns because of that, actually. And so these elements will all react very similarly because of their valence electron number, okay? The same can be said for the second column. Here's the second column here. This is magnesium and calcium. And again, similarities between the atoms are that each of the valence levels have only 2 valence electrons, even though calcium has 3 total, but the valence level looks very similar between the two, and that's why they're so similarly reactive. And we can actually continue this on across the table. So we're starting at boron right here, and boron, you can see, has 2 levels. Its second level is its valence level with 3 electrons. Aluminum is very similar to that, even though it's got 1 more energy level. Its outermost level has 3 valence electrons. See how that works? Carbon and silicon are the same way with 4 valence electrons. Nitrogen and phosphorus are the same with 5 valence electrons. Oh, I didn't do oxygen here. Oxygen and sulfur are the same with 6 valence electrons. Fluorine and chlorine are the same with 7 valence electrons. Oops, I didn't do these right either. Here's 7 valence electrons. And then our noble gases over here, neon and argon, they are similar with 8 valence electrons. And 8 is that magic number. Remember that we try to get 8 electrons in the valence level to achieve stability. Now I want to come back to helium in just a minute because it behaves just like these other noble gases, but it's got a little bit different way of doing its dot diagram. So we'll come back to helium. Okay, so when you do a Lewis dot diagram, there's kind of a little method I want you to do. You start off with just writing the symbol, and then you take the number of valence electrons from the Bohr model and you place them around the symbol, and you do it in sort of a specific way. You start at the top, then you move to the right, the bottom, and then the left. And really, that's not set in stone. The real thing you have to know is that each place on the symbol needs to receive a single atom or a single electron before you make a pair of electrons. So with a carbon atom, you'd start at the top, move to the side, move to the bottom, and move to the right. Those are the 4 valence electrons in a carbon atom. And what's really cool about the periodic table, if you think about this is column number 1, column number 2, column 13, 14, 15, 16, 17, and 18. Okay, so the numbers at the top of the column are really significant because they tell you how many valence electrons are present in the Lewis dot diagram. In the first 2 columns, it's just 1 and 2. But over here, when we start talking 13 through 18, just think about the number that's not the 1. So 3, 4, 5, 6, 7, and 8. And that's represented here by these Bohr models here. So boron has 3 valence electrons, so does aluminum. Carbon has 4, so does silicon. Nitrogen has 5, and so does phosphorus. 6, 7, and 8. Okay, makes sense? And so even though these are technically 13, 14, 15, 16, 17, and 18, just think of them as 3, 4, 5, 6, 7, and 8. Sound good? And so every element in that column is going to have a consistent number of valence electrons, and its Lewis dot diagram will look the same. Okay, so let's do a little bit of practice. So oxygen. Oxygen is in the 16th column, which means we have 6 valence electrons to account for. 1, 2, 3, 4, 5, and 6. Now each position around the symbol, the top, left, bottom, and right, each one of those positions can only have a maximum of 2 electrons, okay? For a maximum total of 8. And that's reserved for the noble gases. Nitrogen is in the 15th column, so we take our symbol, 1, 2, 3, 4, and 5. 1 pair and 3 singles. Magnesium is in the 2nd column, so its symbol just gets 2. Argon, here's a noble gas, so argon is in the 18th column, 18th column, and its symbol AR. 1, 2, 3, 4, 5, 6, 7, and 8. That is a very, very happy atom. This having 8 electrons in the valence level, that's a very good thing. As a matter of fact, you know, when we've talked about ionization, and when oxygen will gain its 2 electrons, it will look just like neon. And when chlorine gains its 2 electrons, it'll look just like argon. So here's chlorine. It's also in the 16th column, just like oxygen was. So it's symbol, and then it's 6 electrons. And you can see how similar the argon and the chlorine dot diagram look. If chlorine just managed to get 2 more electrons, it would have the same valence structure as argon, and that's what elements try to do. They try to become stable like those noble gases. Boron is in the 13th column, and so it's symbol and 3 dots. Okay, now helium. Helium is the special case I wanted to come back to. So helium is in the 18th column, but it only has one electron level. It's only got one level of electrons, and you for sure can't put 8 electrons into that first level. So helium is this special case where it's got a pair of electrons in one position. And so here, the way you would do this, even though it's in the 18th level, it has what's called a stable duet, and we talked about that earlier in a previous video. So its dot diagram looks like this, with a pair of electrons at the top of the symbol. Okay, so that's how Lewis dot diagrams work. Hope that helps.